So thank you, Louis and Omer, for setting this up. And also, I think we need to thank Starkware for the pizzas and stuff. So thank you very much. Let's give them a hand. Why not? If you're holding a beer, you are exempt. That's OK. So there's two ways to go about. This group is named Zero Knowledge TLV. So my talk is really about zero knowledge from the perspective of newbies coming into this world. So I'm I'm an immigrant into the crypto world. Originally, I come from cyber. And so I'm a colleague of Omer at Kaizen Network. And previously, I've been with Imperva, Orado, Microsoft. And thank you, Microsoft, also for hosting us today. OK, and so a little bit about Kaizen Networks. Just a few weeks ago, we announced that about our funding round. And we are hiring, so check out our website, mostly currently for designer and programmers. But if you are interested in this field and you are good at what you're doing, so please shoot us an email, and we are very open to get on board new and talented people. So what are we going to talk about today? We'll give a short primer. Everything will be short. It's 30 minutes talk. So we'll talk a little bit about elliptic curve cryptography, the motivation for it, and I will use a metaphor that I learned about and I really like a lot. I know not everyone likes it, but I like it. It's learning elliptic curve with billiards. And then we will describe also Diffie-Hellman on elliptic curve, ECDSA, using the double billiards metaphor. And finally, we'll employ all this knowledge into the understanding of a recently published attack on the pairing of Bluetooth. Bluetooth we use every day with our cell phones and other equipment we use. And we'll show how an attacker is able to abuse a vulnerability in the protocol to conduct a man-in-the-middle attack on Bluetooth. So full disclosure, so I didn't invent the billiard metaphor. It was invented by Nick Sullivan from Cloudflare 5 years ago. I didn't invent or find out about the vulnerability. That's the work of Eli Biam and Lior Neumann from the Technion, fairly recent. All I did is to combine them together, and you can read it in the blog, so you don't really need to stay in this lecture. You can go home. And also, I'm a very bad billiards player. So, but just not to discourage you too much, a couple of guys found that that explanation to be interesting, including Dan Kaminsky, at least the guys that are coming from the cyber world, very known researcher in that field, found a very famous DNS vulnerability and others. So let's start with the beginning, and let's talk about elliptic curve cryptography. So why elliptic curve? So elliptic curve is a public key asymmetric cryptography, and based on hard problems that are easy to do but hard to undo. So in a way, functions like exponentiation and logarithm that are easy on one direction but harder on the other direction. And what is the motivation of it? Well, at least when I studied, which was in the 1990s, then I was taught all about RSA. So we already have RSA, and why do we need another asymmetric system, a cryptography system? Well, there are all kinds of trade-offs, but one of the interesting trade-offs is in elliptic curve, you can achieve the same level of security with shorter keys. So there's a table here by NIST that shows that ECC keys, elliptic curve keys, are much shorter than RSA keys for the same level of security. And it, as you can see, as the security, and it only gets better if you want to get more security. So this is a good motivation in places that need short keys. For example, in communication, short keys are important. And also in cryptocurrency, we want to keep things very succinct if we can do it. So let's start with our billiard metaphor. So what is the billiards table in case of elliptic curve? It's the elliptic curve itself, and it's just an equation. And the figure in the red is the elliptic curve. And what you do with the elliptic curve, you do billiard shots. And this is the way you add points. So you want to add A plus B equals C. So you shoot towards, you put the ball on point A, shoot towards point B. When the ball hits the curve, it bounces to the other side of the curve. And this is the result C. So if the animation would work, oh, miracle. So, and that goes on, and they keep adding points more and more. So this is the basic shot. So to add A to B, shoot towards, put the ball on A, shoot towards B, and the result is C. OK. Now there is a trick shot. It's when you want to double a point. So when you double a point, so the point B is actually point A. So what does it mean? If we want to use the recipe that I told you before, so how can you shoot a ball from P towards P itself? What does it mean? So if we remember our infi classes, so we will take a point P tag and move it closer and closer to P, and we can see that it comes closer and closer to the tangent of P. So we can say that when you want to double a point, then shoot in the direction of the tangent to the point, and when it hits the curve, go down or up to the other side of the curve, and this is double the point. So we know how to add 2 points, and we know how to double the same point up to this point. And one last thing we need to know is what happens if B equals minus A, if the opposite. So we're following the recipe. We place the ball at point A. We shoot towards point B. But when the ball hits the curve, it bounces to the other side of the curve. But it never touches the curve again. So what we do that? So we artificially stop the ball at the end, and this is the point in infinity, which can also be, you can think about it as 0, and it acts very much as you would expect from a 0 in with the usual algebra. So I think we have all the ingredients to play bizarro billiards. And this is our motivation here is to find a problem that is hard in one direction, but easy on the other direction. So we have a bizarro billiards. There are 2 players. There's the shooter and the guesser. The shooter enters the game room alone, and the ball is placed on a known point P. It's known for both players. And then the shooter chooses how many times to successively shoot towards the same point, P. So we know how to shoot it, to do doubling of a point, so it's easy. And when the shooter is done, the guesser enters the room and they see the final place of the ball. And now he has to guess how many times the shooter had shot the ball. So let's think about the complexity now. How hard is it? So for the guesser, they must replay the game because they are able to do so because they know the starting point. And just playing it shot by shot until they reach the final point. And then they know how many times they struck the ball, and they know the answer. So to do that, it's order of n, or if you will look about the representation of n, it's 2 to the L. So if we look at the binary representation. So it's hard. It's exponentially hard. However, the player, they have an advantage because they know in advance how many times they're going to strike. So they can smartly divide that number into additions and doubling. So double and add. So for example, if I know in advance that I'm going to shoot 100 times, I can now break this number into a series of doubling and adding. So only 6 doubling and 2 additions. And if you look at it, it's very much related to representation. There's a simple syntactic algorithm to take the binary representation. Wherever there is 1, do this, and wherever there's 0, do that. And so you can see the complexity is O of log n or linear in the representation. So very, very easy. You can't beat linear by much, right? So we found the hard problem we are after. So it's very easy for the player, but very hard for the guesser. So I hope that makes sense to you. OK. By the way, the official name of it, so we want to call it the billiard problem, is the discrete logarithm problem over elliptic curve, ECDLP. Now let's talk about the elliptic curve Diffie-Hellman, ECDH. And Diffie-Hellman also exists in the RSA, originally comes from the RSA algorithm, and uses allows secure key exchange in the presence of an eavesdropper. So we have an eavesdropper, and Alice and Bob wants to communicate but Eve is in the middle, eavesdropping. So how do they can exchange and reach to have a secure key, same key on both sides? How they can agree? So we can do some kind of what I call that double billiards. So Alice plays our bizarro billiards game. Ball is placed on a known point. Then she strikes S1 times of her choosing and sends a photo of the table of the finite point to Bob. And then Bob starts his game from that point onward, and he strikes S2 times and sends the picture and reaches the secret key, which S2, S1 times P. And on the same time, Bob starts a new game, starting from the original point, and strikes S2 times and sends a picture of it to Alice. Alice then can strike S1 times from that point. And since we use the quality of multiplication to be associative, so we can change the order there and also open the parentheses there. And so they both reach to the same final point, and it exists for both Alice and Bob, and Eve learns nothing. So just to be a little bit more formal about that, so S1 and S2 can be called the private keys, are called the private keys, and the public keys is S1 times P, and S2 times P, the public keys of Alice and Bob. So if we'll do a small demonstration, so Alice is striking S1 time and sends the picture to Bob. Bob strikes S2 time and sends the picture to Alice. And then each of them are striking again using the private key to strike again on the final according to this picture, and they reach to the same final board setup. So it's identical on both ends, and Eve learns nothing because so Alice and Bob didn't learn anything about the secret key of each other, because as we said, going back is hard. So if you have S1 times P even if you know P and you know S1 times P, to do the other way around and get S1 is a hard problem. And Eve didn't learn, she didn't learn about S1 and S2, even though she saw the pictures, because again, going back from S1 and S2 to, going back from the S1 times P to S1 is hard, and it's the same for S2. And also, she doesn't know what is the final shared key because it wasn't shared. It was sent over the communication line, but calculated on each side separately. Okay. Yeah.
Always assume everybody uses the same curve?
Yeah, this is very important. The curve is also known. The table is known. And for
people use different curves, or there's one good curve?
So there are all kinds of different curves that have all kinds of security and maybe complexity and interesting things you can do about it. But one of the known parameters of the system must be the curve. A very good question. Sorry for not saying that. And in fact, we'll see that the attack, if someone is changing things in that curve, and that's the direction of the attack, then in most cases it wouldn't work. So we'll see about that. But yeah.
Actually, the problem assumption is different than the discrete logarithm itself, right? I mean, you have two exponentiations. It's the computation of the no?
So what happens? So of course, I encourage you, everybody that knows that is of course. I say go read the textbooks, but it's I think unless I'm mistaken, Omer, you can correct me on that, is that it's a multiplication over the elliptic curve. Okay.
Depending on the notation, no?
Okay. Okay, so let's go over what happens if the attacker now is not a passive eavesdropper, but a man in the middle. So what can happen, the attacker can play Diffie-Hellman with either of the sides and get to agree on shared key, but it's not shared Alice and Bob, it's Alice and Mallory have a shared key, and Bob and Mallory have a shared key, and Eve can be man in the middle and play with the communication between them. So there are secret key is created, but it's not the same for Alice and Bob. So so for Mallory, if the attacker is man in the middle, then Diffie-Hellman does not work, and to mitigate that, there needs to be a way for Alice and Bob to compare their shared key and to make sure that they have the same shared key. Because if they were able to do so, they would see that there is something wrong going on because they have different shared key. Each one is shared with the Mallory. Okay? So with that, with this basic knowledge, we will end with a specific example of an attack on Bluetooth pairing. So Bluetooth, we use that every day. For example, to have a speaker phone, a hands-free phone. And since Bluetooth can expose private data or let a connecting party control the Bluetooth device, there needs to be encryption. And there's a pairing process is used to identify a specific device. And this pairing process is using ECDH, elliptic curve Diffie-Hellman, to create an initial key, very much to create a common key between the parties. And later, KDH is verified using the Bluetooth pin code. So when you enter the pin code, it uses that knowledge that is to make sure that all sides has the same private key, and so it's not exposed theoretically to man-in-the-middle attack. So, but in this protocol, KDH is only we're only using the x coordinate. This is a point, and we only take the x coordinate of it to be the key. And the spec does not mandate y coordinate verification. It shouldn't be a problem because we're not using y, right? But what the attacker might do, and this is the vulnerability, is Mallory abuses the fact that y is not verified, only the x. We just, in the end, Alice and Bob just make sure that they got the same x coordinate, and specifically they don't make sure that they are working on the same curve. And the attacker is keeping the same x coordinate, but zeros the y coordinate, which effectively puts the point on the x axis. And so if we go there, of course, this point is not on the curve, and validating, making sure, just plugging in the numbers into the graph, into the elliptic curve equation would show that, but it's not mandated by the spec, so nobody does it. So what the attacker gains by putting the ball on that point, so now each of the sides needs to, as we said, they get the picture and they're playing a round of bizarre billiards with that. So the ball is placed on the x-axis, and we're doubling the point, shooting the ball towards itself first. And so the tangent in this point is just straight line going to the point of infinity. So on every shot, either the ball goes to the point of infinity, and then when you add the point to infinity on the next shot to the point P, it becomes P because it's like a zero. So on every shot, either the ball is placed on the point of infinity or it's on the point P. Okay, so if we plug it into our problem, so then we have Mallory in the middle, and she keeps the same x coordinate, but zeros the y coordinate. And if S1 is even, and S2 is even, they both reach the same point, which is the point of infinity. And Mallory wins because if they are both even, then the secret key on both sides is the same and has the same x coordinate. But in any other case, they fail. So 25% of the times Mallory wins. But she doesn't care because probably if you want if you fail, you probably try to pair again. So eventually, Mallory will win. And also, there is a smarter attack using that property in a more active way to increase the winning rate of Mallory to 50%. So with that, I conclude. And so if you have a question, please right now, or we're short on time, so shoot me an email or send me or tweet to me. And remember, KZan Network is hiring. So thank you for coming.